undergrad stuff?
Yeah, like OSU, they would probably accept like the first two and then you could take the third. The only issue, like I said, is when you transfer to semester universities.
Yeah, okay.
Thanks. Yeah, and then you're stuck taking half a year.
I'm trying to like, it's expensive, so. See?
So I assumed that you were going to be able to.
You had mentioned in the beginning of the term that like you often drop one of your students, like you'll drop a quiz. Are you still planning on doing that? Can I ask you a question? This is from the lecture, actually. So on this question here, I was just curious about this. Like, there's 1 carbon and 1 CO2. So is it just because it's just 1 to 1 that it's the same moles?
Yeah, so basically all your carbon gets converted to CO2.
Mm-hmm. And that's why it's all. And so if any time it's like that, that's always just going to be a 1 to 1 kind of.
Yeah.
And it'll be the same amount of like the moles of this is the same as for carbon. But does that, how does that account for the O2 here then?
What do you mean?
Like, because like this right here, this number was the, in my brain, it was the mole, let's see here, moles of CO2. But then it's also the same for just carbon.
Right, because
Even
you've
though the
added
oxygen is not there.
oxygen to it, right? So
Yeah.
you've added some amount to it. But what you're still saying is all the carbon becomes CO2, right?
Yeah.
So every equivalent makes that many CO2s. And then
Okay.
obviously, right, you have to add that much oxygen, but we're not dealing with that in there.
Okay.
But yeah, that's where you go back and do the mass subtraction later, right, to figure out how much mass was added of oxygen to quantify it.
And so that would be, but we didn't do that in this.
Yeah, because that one,
I was just specifically asking about that.
yeah, and this one didn't contain any oxygen in there, so we didn't need to quantify it. We didn't care. We weren't asking about that to find the original formula.
Okay, thank you.
Last week's homework, the 13, or I assume
Not on me, but I could get it later.
Yeah, I was looking at the map, it's pretty far.
Gonna be what? I did not say that. I said it'd be in the same format as the midterm, so first half multiple choice, and then second half open note, but free response. So half of it will be open note. All right, let's go ahead and get started. So a couple of announcements before we dive into the rest of our chapter. So first of all, right, hopefully while y'all are on vacation for a few weeks, you'll remember to look at this REU site if you haven't been doing that already. So there's some good opportunities, and I'm noticing deadlines are coming up. So I limited myself. Obviously, y'all don't have to. I just, for y'all's purposes, I went and searched West Coast. There's West Coast, Best Coast, so California, Oregon. Notice this popped up, right? Caltech. That's actually where I did my undergrad. I know we have some young budding physicists in here, so you probably want to apply for this. So this is summer 2025. Applications are being accepted now until January, so I would look at that. So that's pretty cool. And then obviously other opportunities. I didn't go through everything, but that's what you need to do to figure out, right, potential research opportunities. This is the best way to get experience. Got some opportunities at the Monterey Bay. So it looks like applications are opening for 2025 summer, so I would get on that. So looks like this Monterey Bay one just opened up So December 9th, oh, it's not even open, my bad. So, right, get on it, be the first one, so your name will be at the top of the list, right? If there's recommendations, I'm happy to write y'all recommendations. Very important for your career to get in on research and doing stuff. So tons of opportunities to look for, so make sure you're checking this out. I'll post a link to that. And then, so let's just briefly look at the SOU trip. So did y'all see the announcement I made on Blackboard? Yes, no? All right, so, all right, there's an announcement. Oh, gosh. Sorry. I don't know why mine looks terrible, so now I can't tell. There it was. And so I reposted the waiver if you haven't filled that out, and then I also posted this map, so if you look at the parking map, you can see where we are going. And so just a quick recap of the instructions. So notice first you have to go to a meter in one of their public lots first, and then follow these instructions, right? Put in your license plate, and then go down and see the day pass code, and then enter in, right, that nice code that they have provided for our trip, especially, so that is for us for that day. And then once you get it entered in these public parking lot meters, then their suggestion was that you could repark in lot 27, so that's right in front of the science building where we said we were going to be meeting. And so I posted the map there, so there's the science building, so there's Siskiyou Boulevard, and so find your way there. So there's lot 27, again, right across from the science building where they suggested to park, but obviously there's other lots. And then, right, notice the map has the visitor meter parking spaces marked, so again, you have to go to the metered visitor spot, so maybe one of these locations before traveling or attempting to find parking at 27. And then I was telling people maybe try to get there, you know, around 8:45. If you're planning to arrive by bus or car, you know, give yourself time to park and enter in the code and all that stuff, and probably print these instructions. And again, long sleeve shirts for safety. So don't forget your clothes, proper clothes. Sorry. I don't know why it won't remember my mapping settings all of a sudden on the last week. It's given up. All right. So yes, don't forget your pants. And again, they're long sleeves requests. I am saving one of my shirts for that day so I can wear my long sleeves as well and be compliant. And correct, yes, parking should be free then with that code. So that's the whole point of the code, that you have free parking, and that is good for the entire day at SOU. Yeah, so the code's on Blackboard, so just, it was an announcement. So it's on the announcement page, and then you can ask me.
Is it the same with the writing thing?
The writing thing is posted as an assignment. So the writing assignment should just be posted. I try to put it at the top so people could find it, along with the extra credit trips as well as the top, so you can submit those. Or again, if you submitted them by email, I know that. I just haven't gone through and.
What's extra credit that we had to watch?
Yeah, so that's the I1 here. And so if you click on that, it takes you to the YouTube video, and then I was just asking for some short sentences. All right, any other questions? Okay, everybody's ready for the field trip that's going, and then again, everyone is still welcome, no limit. Just make sure that I get your waivers because RCC does not want to get sued. And so people offering rides in the chat as well, so right, feel free to coordinate that, or like I said, bye, so. Oh, the waiver? Yeah, that's just a general waiver. So yeah, you can fill it out or just give it to me. Just put like SOU trip, chemistry, you know, all the details don't matter, just as long as you sign your life away, of course. Yeah. I think there should be enough in the back. If not, I'll get some extras. All right, let's finish up our chapter then. Oh, and then I did also post, I don't know if people saw that, but there's, I think, a review as well under week 10 of just the concepts. So you can look over that so you can prepare for your exam. And like I said, we'll do review next Tuesday, exam on Thursday. All right, so then, right, we've been talking about enthalpies and how to calculate, right, these different reaction enthalpies, right, whether they're exothermic, endothermic. And so, again, we wanted to address the question of, well, how do we determine these values? And so, okay, we determine that either we can do this experimentally, right, through a number of different pathways to get to our overall desired pathway, or the next way we can do it is by examining our bond energies. And so, of course, chemical reactions involve breaking bonds in reactant molecules and then making new bonds to create our products. And so we can calculate our change in enthalpy then of our reaction from comparing essentially our income, so how much it costs to break our old bonds, because again, that's going to be positive, so we have to put energy in. And then it's thermodynamically favorable to create bonds, so then we'll get our income, so negative, right, exothermic energy. So we'll be comparing that essentially. And so this is, again, just how it is calculated, so we can understand it for our purposes. And so all these standard values are calculated in the gas state. And this is using a homolytic bond cleavage. And so this is just what we would also call a normal bond. And so we can, think simply, such as H2. And so if we were to break that, and so I'm going to use little half arrows to indicate single electron movement. And so then it would break, again, homolytically, where each atom gets an equal number of our bonding electrons, so half of our bonding electrons. And so all that to also just point out that, yes, you could also technically have heterolytic cleavage, so we at least should define that. If I could spell hetero. And so that would be in special cases. And so one of those would be in the case of boron trifluoride and ammonia or some sort of nitrogen-based compound. And so in this bond, this is actually not a normal bond. So, right, we can examine that. Let's think back to the Lewis dot structure of ammonia, right? So nitrogen has those two lone pairs. And so that's what's going on here. So this is actually a dative bond. And if we wanted to show this properly, it'd be best to write it like so to show that, yes, nitrogen is donating both of those electrons actually in this bond. So therefore, when it cleaves, it does not cleave homolytically, but rather heterolytically, where those two electrons go back to that nitrogen. So again, we won't really be dealing with this scenario. That's just this is what can happen. There are special bonding scenarios like this, and so that's where that would apply. But again, most of the times in our classes, we're going to just be focusing on this homolytic cleavage, where it is our normal bond, and they're all contributing one electron. And so then this is where we get a standard table of bond energies. And again, this is just average. And so we can at least just appreciate some general trends. So obviously, right, we have single, double versus triple bonds. And so obviously more sharing of electrons is going to be a stronger bond. And so much more energy contained in that bond. So again, not expecting you to know numbers, but just, okay, there's some general trends. We can also see the effects of radius. So we compare bromine, 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 chlorine, and bromine, fluorine. So of course that bromine-fluorine bond is going to be a little bit physically closer, right, since fluorine is smaller. And then that's reflected slightly in that bond energy, with it being a little bit higher there. And of course, this chart is given in kilojoules per mole, but it could be, right, in electron volts. It could be in different units, right? It could be per atom. So just watch whatever chart and reference material you are looking at. But mostly for chemistry, it'll be in kilojoules. But again, if you start looking at different references, just check the units. Oh, and then a quick note. So we have C double bond O here. So this would be, right, and just some compound, whatever, normally. But then it does point out that we have a special value for CO2, so higher. So that is significant enough that it points it out, so we should use that. And so now we can look at kind of graphically how we can analyze this. Okay, so we're looking at this reaction. And well, let's see what we're trying to do. And we can write out our reaction here, what's shown. And so they're showing us we have methane here. And now I'm going to try to draw it more to emphasize the bonds rather than the geometry, because I want to see what are we breaking, what are we making. Okay, so we have methane and chlorine, and then it looks like we're going to form chloroform. Oops. Oh. And then hydrochloric acid. And so then we can start kind of pointing out what we have to do. And so what I mean by that, right, so look at what changes. So one of our carbon hydrogens becomes a carbon chlorine. So we're going to have to break this bond. And then we'll be making, right, our new bond. And then, of course, we're going to also have to break this chlorine-chlorine bond and then form an HCl bond. And so that's what's represented here graphically, right? So now we're saying, okay, we're going to have to put energy in. So that's an endothermic process, right? So putting energy in, right? Obviously going up on the y-axis. So we're breaking that. And then let's quantify that, since, you know, they just did it visually, but let's put some numbers in there. So we can go to our chart. So a CH bond is worth 414 kilojoules per mole. So let me just write that down. So 414 kilojoules per mole. And then let's check how much that chlorine-chlorine bond was. Where's chlorine? There it is. So 243 down at the bottom. So 243 kilojoules per mole. And so we could add that up as well. Again, just to see, right, the total energy that we put in just to break those bonds. So 414 plus 243. All right, so now we're at 657 in. So put a bit plus sign there, kilojoules, again, right, for breaking our bonds. That's what's shown here visually. And, okay, so now we're up here at this weird, transition state or whatever, graphically. And, well, now we need to figure out, right, the end process. So like we identified, we're going to make that carbon-chlorine bond and that HCl bond. So let's actually get some numbers so we can see that it's going to be lower. So where's our carbon-chlorine value? Help me out here in blind. There it is. So 339 for carbon-chlorine. So 339, and again, right, thinking a big fat negative, we're getting this energy back out. And then HCl, so how much is that bond worth? So 431 kilojoules. And so sometimes I like to just add these numbers first, right, so we can compare. I'm just, again, right, kind of putting our signs. Again, we're getting that energy back out, exothermic, so plus 431. So then a total, right, of negative 770 from making those bonds, right? So we put in 657 compared to 770, so now we can add those two values to figure out, right, our overall change in entropy. And so we get that this process was exothermic with negative 113 kilojoules. And so they didn't give us a value, right, but we at least see it was exothermic. So we were able to calculate that change in enthalpy there. So not too bad, these processes. And so see if you can try that now for this one. So I'm going to have to do some scrolling up and down. So first, I would just write out the reaction. But then after you just write out the reaction, I would draw it out visually, right? So you can see how many bonds am I making and breaking, just like you did for the lab, right, with the water. So we have 1 mole of methane plus 2 moles of water, give us 4 moles of H2, and then 1 mole of CO2. So see if you can calculate your change in enthalpy. So get that reaction. Yeah, I'm just giving people one more second. Try to write down the reaction. And then I'll try to scroll up so hopefully we can see that chart. Hopefully everybody's got their vision checked.
look at the example you gave before this? Please, thank you.
So let's kind of see where we're at. We can help each other finish. And so like I was saying, the first thing I would do, especially when you first start approaching these problems, is, maybe just draw out really explicitly what's happening. Again, I'm not caring about geometry so much. I'm just trying to visually see what has to get rearranged. And I'll draw out, right, 4 H's. Again, and our CO2. All right, so now we can really kind of see what has to happen. And so what do we need to do? What do we have to break? Yeah.
You've got to break a bunch of hydrogen bonds.
So we got to break. So you mean all these CH bonds, or?
Yeah, the OH bonds.
So we got to break all these CH bonds, so 4 of them. And right now we can actually, okay, 4 CH bonds. And then a bunch of OH bonds, which is 1, 2, 3, 4 OH bonds, right? So make sure, again, you count that properly. So now 4 OH bonds. All right, excellent. So let's start with that. So what was the value of the CH bond? We get that. I know it's kind of hard to see. So 414 for CH, and then of course, right, we'll have to multiply that by 4. So times 4 plus, what was our OH bond strength? 464. And then again, right, times 4. And so I'm just going to stop and do the math real quick, right? Figured out how much energy did we put in to break all those bonds. So 414 times 4 plus 464 times 4. All right, so then I get 3,512 kilojoules in. So there's my big fat positive sign, right? So again, we have to put energy into the system. So let's figure out our profit, essentially. So how many bonds, what bonds did we form now? So a bunch of H2s, right? So 1, 2, 3, 4 HH bonds. And then what else did we form? So our CO2, and then of course that was our special number, and then it's 2 CO2s of these special CO bonds. So right, just meaning we have to use 799 for that CO value for CO2. And then, so 799 times 2. What was the HH value? Get that one. So 436. So 436 times 4. And so now I'll add those up, right? Figure out how much energy we got back out. Plus 436 times 4. And so I get 3,342. Question? No, I mean, that's not why it's considered a global warming gas, but yeah. We shouldn't go down the CO2 rabbit hole today. I don't want to go there. That's all I'll say. All right, so that means we get negative 3,342 kilojoules right out. So, okay, let's figure out the net overall energy of that. So negative 3,042 plus 3,512. So again, make sure you get your signs properly. And so overall, though, we had to put in 170 kilojoules for this process, right? So now we can say, okay, this was endothermic. Energy was required overall. Questions about that?
So when you form a bond that's endothermic, it takes energy to form it. Does that energy have to come in any specific form?
Well, so we're mainly talking about heat. So yeah, like usually these are changes in enthalpy, so it's always just a change in heat.
Do you do so with like light or sound?
So like potentially, right? So there's some like UV active reactions, so that gets into like different sorts of chemistry. All right, so let's do our last little bit. And so getting into specific heat just a little bit. So we won't get into state changes, but just, right, how much heat a particular material can hold. And so, right, this is kind of related, obviously, to our experiment and calorimetry and what we're doing, right? So this is essentially how we measure enthalpy in a lab. Again, right, we were limited by our little experiment. So I mentioned perhaps if we had a better calorimeter, right, something that was made out of metal, and then we could actually perform the true combustion reaction, maybe we could have measured that enthalpy directly. But we could certainly not have burned that magnesium in our styrofoam, right? So that's why we had to go through those indirect reactions. And so with that, right, what you were doing with that in those calculations was measuring, right, the change in temperature. And that change in temperature is related to our heat then. And so, right, obviously, let's start off with, okay, well, what were we trying to measure? So obviously, right, we're measuring whatever energy is being given off by our reaction. Again, if it was exothermic, so right, we're going to be feeling that hot. Obviously, you could also measure it being cool. So you're measuring, right, your change in temperature. And right, like we mentioned, whatever is happening to the reaction is the opposite of the surroundings. So that's all that's meant by that case. And okay, well, what did we do in our experiment? Well, that's why, right, we had our mass of water, right? So we were trying to essentially change the temperature of water. And so water is beautiful for so many reasons, and one of those, of course, is being its high specific heat. So again, that's why West Coast is the best coast, but any coast is the best, right? Because you have the large body of water keeping your temperature regulated. And so that's also why we had to measure our water very accurately. So if you remember, we measured the HCl using that volumetric pipette. So we were being accurate with our mass, right? So we could have, obviously, treating it with 1 gram per centimeter. So then we got our mass, and then obviously you guys measure your delta T, right, to figure out your heat that was evolved in the reaction, which of course, right, you then took that heat, divided it by the moles to figure out your molar enthalpy of your reaction. And so that's what it says here, right, to divide our delta H per mole, divide by moles. So yay, we did that. So we did that whole process. So now we're just kind of reappreciating the math with it. And so now here is, right, one of your experiments that you did do. And so, right, you did this in lab, you witnessed this, you saw how exothermic this reaction is, so dissolving magnesium and HCl. And so here it says we combine 0.158 grams of magnesium metal with enough HCl to make 100 milliliters of solution in our little coffee cup calorimeter. And so it reacts, and so our solution rises from 25 to 32.8 degrees Celsius. So see if you can find the delta H of the reaction. So right, we want our molar enthalpy given this data. And so we can use, of course, 1 gram per milliliter as the density. And then there's our specific heat of water. And so notice, right, the units on these also kind of tells us, again, what we're doing, right? Go back to our formula. It's just specific heat times mass times delta temperature. Check your units out on your specific heat, right? They should match. And generally, specific heat is always given in this, but again, right, always check your units. You never know what reference you're going to be looking at.
I've noticed in physics that the general constant for mass needs to be most often is the kilogram. Would you say that the gram is sort of the standard for chemistry?
Yeah, so that's a big difference between chemistry and physics right there is, yeah, they're always talking about kilograms, we're talking about grams. So yeah, so again, just watch those units, right? So again, looking at that, we notice we should be in grams for this based off of our specific heat. So again, just appreciate too that water has a high specific heat there. And so it's joules per gram degrees Celsius. So again, teasing back out that formula. So see if you can calculate that. You should be able to calculate it though. That's the whole point of the unit. Dimensional analysis. And dimensional analysis is your friend. That's so when you blank out on the exam and you're like, what's the formula? You look at the units. Now we'll go back. So do we calculate just Q, so heat given off for our reaction? So what do we need to plug in for Q?
Is that the same as the change in temperature?
No, because what's the change in temperature?
Like 7.2 degrees.
7.2. So, right, so we have our delta T, so 7.2. And so just to point out, because this may come up on your exam, hint, hint, right, our change in temperature in degrees Celsius, what would it be in Kelvin?
The same, right?
The same, excellent, right? So don't forget that they go up by the same, right? So if it's a 7 degrees difference in Celsius, it's a 7-degree difference in Kelvin. So don't let me trick you on the exam. All right, so we have our change in temperature, right? We have our specific heat that's telling us our formula, so joules, gram, degrees Celsius. So, right, I'm going to go ahead and plug in my 7.2, since that was, right, the change in temperature that this is occurring over. And then what is the gram amount, though? So 100. So, again, beautiful thing about water, we don't have to think about it, right? So you can just do the math. So gram per milliliter. So obviously, milliliter cancels out. So yay, 100 grams. So 4.18 times 7.2 times 100. And so then we get, right, our change in Q for this reaction is 3,009, so right, joules. And so what's our next step? So how do we figure out, right, molar enthalpy? So let's do that, right? So this is, and so, right, we want to kind of relate this. Okay, that's right, right? Again, this is what we did in lab. Okay, we said if we dissolve 0.158 grams of magnesium, it's going to evolve this much heat. And so let's figure out, right, the molar amount then. So again, we can just quantify it in a different way. So 0.158 grams divided by, what is it, 24.3? Somebody help me out. What's the mass of magnesium? I can't remember, it's 24.3 or 03?
24.305.
Oh, 305, okay. Right, so now we have that many moles. So 0.0065. So, right, we can, obviously, right, they told us to divide. But I want you to think about this. Again, right, what are we really saying? Set up a proportion, if that makes more sense to yourself. So we're saying, okay, if we have 0.0065 moles, right, that's giving me, and let me just convert this to kilojoules, essentially. So that'll be, right, 3 kilojoules. I just don't want to work with silly, crazy numbers. And so we could set up a proportion. So if we want to know the molar amount for 1 mole of magnesium, right, how much energy is released. So that's one way to think about it. And so that's telling you, oh, right, that's why we divided. So then we can take our 3.009 kilojoules divided by our molar amount, solving for our proportion. So we should get about 462 kilojoules.
What is the 1 mole represent under the moles of magnesium? Is that for the whole, or, yeah, what is it?
This?
Yeah.
Oh, I was just setting up a proportion, yeah, to get to 1 mole of magnesium, right? So I just wanted to go back to this reaction essentially, right? Pulling it in terms of 1 mole of magnesium, again, based off of how much that is. So we effectively, right, did the same step. I just think showing it in the proportion is maybe a little more powerful, right? Because again, you measured that directly. You can do that and say, yes, 0.0065 moles of magnesium evolved that much heat. I quantified that, I measured that, so therefore I can calculate, right, the amount for 1 mole. Because we said that it was dependent on, right, the amount. So we've been seeing that. Questions on that? Is that kind of making sense? Yeah, so then, right, it's kilojoules per mole then, right, is the change in enthalpy for that reaction. So that's what we found. And so, right, if we wanted to verify that, you know, we could try to verify that by a couple of different methods, right? You could think of how you could verify it, right? You could verify it by bonds broken and bonds formed. You could try to verify it by, right, looking up their standard entropies. So you could look up, well, this is going to be 0 and this is going to be 0 because they're in their standard states. So you could compare what's the standard enthalpy of formation of magnesium chloride, right, minus 2 hydrochlorics. And you should come up with, again, relatively the same answer. So it's all, again, path independent, so there's lots of different methods to calculate and kind of verify that. Right. Any questions? Do we want to try to, we could try to verify that. No, so Hess's law would not apply to path dependent. Correct, because heat enthalpy is a state function. So, right, something that is not a state function, like again, work, right, because work is path dependent. So then, yeah, you would not be able to use Hess's law because then you would have to, right, actually measure out the path. So then path would matter, yeah. Trinity? Yeah, I could have made a rounding error. Other questions? Do we want to try to see that? We probably have enough time to just quickly try to verify, again, maybe how accurate, right, this was. Yeah.
Was the density of a solution for the molarity of the solution affect how quick or effective the chemical reaction is?
So the density only really affects the mass, right? But then, so, sorry, what was the second half of the question?
What I'm essentially asking is the number of parts per milliliter of a chemical effect, how effectively it creates new chemicals?
I mean, concentration can affect a rate, right? And then potentially once you start getting into more exotic things, like changing the concentration of different things can give you different products and different ratios. So. All right, other questions, comments? All right, maybe we'll just go ahead and end here then, since we're pretty much at the time. So I do have your quiz. So again, we'll take our break. I can go ahead and pass it out though. Yeah, you have to turn those things in there. Yeah.
It's coming together.
No, like specifically was the Sayette Act.
Yeah. Oh, I can't tell. I know. I don't know. The next one, there's